Hello folks, hope you're enjoying your weekend. Here's the new video for the next unit. It'd be Unit 3. Take a moment to pause it and write down the learning targets, please. Okay, so this unit is going to be about our first unit on astronomy, specifically about the formation of the universe. But before we get into what the actual universe is, we have to look at what light is and how useful light is as a tool to astronomers. Some people would say it's the most useful tool. Without light, normal telescopes wouldn't work, but there's other kinds of telescopes that still would. There are X-ray telescopes and such, and radio telescopes. Remember that we see any object, whether it's in space or right in front of you, because light reflects off of that object. That allows us to see. Without light, obviously we can't see because there's no reflection of that object. So if stars make their own light, then we can analyze that light from Earth, and we're going to see how to do that just in a minute. So light comes in waves. It also comes in little packets called photons, but that'll be another discussion later. But waves, like so many energy forms that come in waves, have a couple of basic properties that we're going to look at. They have more than two, but there's two basic properties we're going to look at right now. And that's the how long is the wave, called wavelength, and how many waves pass by a certain point each second, and that's the frequency. And it turns out that the wavelength and the frequency have a inverse relationship. That means as one goes up, the other one goes down. So if you'll look there at the picture on the left on the bottom, it shows you what a wavelength is. It's the length from the crest to the crest of a wave of waves. It can also be from the trough to the trough, either way you want to remember it. And on the second diagram, that shows you the relationship between short waves that have a higher frequency or longer waves that have a lower frequency. Basically, if you have a long wave, you can't get a whole lot of those to pass by a given point, in 1 second. But if you've got really short wavelengths, then you can get a lot more by those every second. And remember that almost all EM energy, electromagnetic energy, radio waves, light waves, moves at the speed of light. So the speed is pretty much constant. So you can get less of these by a given point in 1 second, more of these by a given point in 1 second. Wavelength of visible light is usually measured in nanometers. That's a billionth of a meter. So out of the entire visible spectrum, out of the entire electromagnetic spectrum, which you'll see a diagram of that in a minute, we're going to only worry about in this unit the visible part, the part that we call white light, the part that allows us to see, the only part of the EM spectrum that we can actually see. And it's composed of 7 component wavelengths of light: red, orange, yellow, green, blue, indigo, and violet. You may have learned that in grade school as Roy G. Biv. And if you look at the diagram of the visible spectrum, you can see those arranged. And you see on the far end, IR means infrared, and on the left, UV means ultraviolet. Those are not part of the visible spectrum, but they're just outside the visible spectrum. So we can't see those wavelengths with our eye, but they're just very close to each indivisible spectrum. Notice that the wavelength in nanometers increases as it gets towards red. That tells you that the reddish wavelengths are longer than the bluish wavelengths. So if we apply what we just talked about in the last slide, if you have a red wavelength that is longer, the frequency is going to be shorter, smaller. And violet has short wavelengths, so the frequency is going to be higher. So here's a very, very basic diagram of the entire EM spectrum. You can find much more detailed ones on Google, on the internet, but it shows you exactly how small a part the visible spectrum is in the overall total EM spectrum of all energy. I mean, from gamma rays, the stuff from nuclear reactors and nuclear weapons, all the way to the really large wavelengths that's measured in meters, big wavelengths called radio waves. Just a very tiny part of the entire amount of energy in the universe is actually visible to us. And again, you can also see again the violet towards the red end. So there's something called something called spectroscopy, this word over here, that allows scientists to determine the component of a gas or a liquid or even a solid. But we're worried about the components of gas. So when stellar objects like stars give off light, scientists from Earth can figure out what the gases in that star are and the composition of gases in that star based upon their spectral lines as read through a spectrometer. That's a device that actually analyzes the gas, the liquid, or the solid to see what it's made of. And it turns out that not only can light spectra help scientists figure out what something's made of, what kind of gas an object in space is made of, but this is some information that we got from a guy named Edwin Hubble. He determined that the universe was expanding because every galaxy that he looked at and did some calculations on was moving away, and he figured that out by this idea called redshift. Now, redshift is going to be mentioned just in a second. It turns out that these spectral lines would be either the emission or the absorption of a certain element in that galaxy, and then if it's moving away from you, like here's the viewer on Earth, and the galaxy way out in space is moving away from you, then it turns out that those wavelengths of light have longer wavelengths. If a galaxy is moving towards you, or a star is moving towards you, then you have shorter wavelengths of light. So remember, if the red end is the longer wavelengths, it turns out that the light from these galaxies was shifted towards the red end. So if you look at these three spectral lines in a motionless light source versus a receding, moving away light source, then see all lines are shifted towards the right, towards the red end. We call that red shift. So that's based upon a principle called the Doppler effect. And Doppler effect occurs in lots of energy. You've probably heard it in sound waves, and I'm going to demonstrate that audibly, using audio in class. But this diagram does a pretty good job. So here's an ambulance with its siren going, and here you are, and the ambulance is coming towards you. Look at the wavelengths, how short they are. But if the ambulance is moving away from you, then the sound waves are not as compressed, and they have a longer wavelength. Well, something we didn't talk about is that wavelength and pitch of a sound. Short wavelengths means high frequency, that means high pitch. Long wavelengths means low frequency, it means lower pitch. So that's when you get that characteristic sound of an approaching siren or horn or a train horn. I'll demonstrate that in class. So in class the other day we talked about what was the universe. The universe is pretty much everything: time, space, matter, energy. There's nothing that's outside the universe. There's nothing outside the universe. There's just simply nothing. So if we could remove ourselves from the universe, theoretically or hypothetically, sorry, then we would be in nothing. And I don't know about you, but for me, nothing is very hard to grasp. So here's the information about Edwin Hubble using redshift data of galaxies, and that was the evidence that he used to make the claim that the universe is expanding. He mathematically supported that with math that's way above my head, and so basically we now know as an accepted theory, idea, that the universe is expanding, and then somebody later on figured out that the universe's expansion is actually accelerating. It's getting faster and faster and faster as it expands. So just to give you an idea of what we're talking about as far as galaxies, the Hubble Space Telescope, this orbiting space telescope, just a few hundred miles above Earth, takes really great pictures of deep space. This is really out there in space. This was not possible with an Earth-based telescope. And all these little fuzzy objects are galaxies that contain billions of stars. So, how old is the galaxy? Scientists have calculated it to be 13.7 billion years old, plus or minus a few million years. The size can't be determined. They don't know. They think the size is definitely based upon the shape of the galaxy, and right now the three most proposed ideas of shape are the sphere, the saddle, like a horse saddle, and flat. And just to give you an idea, NASA supports the idea of the saddle-shaped universe. So, the Big Bang Theory, creation of the universe. This is a very simple diagram of kind of what happened in the tiny first fraction of 1 second. There was a big inflation, and then matter was created, and then here we are today, 13.7 billion years later. Here's a little bit more detailed timeline. It turns out that just a very, very, very small fraction of a second, the universe quickly expanded, inflated like a balloon inflating. A microsecond, a millionth of a second into the creation of the universe, it had its shape, whatever that shape was going to be, saddle shape, flat shape, whatever. And then 3 seconds after the Big Bang, the basic elements formed. And before that, just the protons and neutrons formed. But then the basic elements formed. And those basic elements, of course, are hydrogen and helium. And then you can see 10,000 years, 300,000 years, 300 million years, all the different things that happens. And then at about 5 billion years ago, our sun was one of many stars created. And then I cut the timeline off there because it doesn't really apply to the creation of the universe, but the timeline goes on to present day, and it's even projected into the future. So that comes from pbs.org if you want to go look at that. So that's pretty much the end of this video, and we'll talk more about this and hopefully clear up any kind of details, any questions you have in class. And be sure you answer the questions that follow this on my webpage so I know that you've watched the video. Enjoy the rest of your weekend.